Hi guys! This video is a compressed summary of our second live session on the SoccerNet-v2 challenge. We present the DevKit and our context-aware loss function method showing some Python code. Once again, big thanks to all researchers who participated in the discussions and questions.
Feel free to join us for our next session on Thursday the 6th of May at 1 p.m. UTC. We will have a talk by Silvio regarding his method NetVlad and NetVlad++. This will also be your chance to ask questions or discuss ideas. All the links are in the description just below. Subscribe to our channel to support us and enjoy. So hi everyone, thanks for joining on this SoccerNet-v2 tutorial. So last week we had quite a successful tutorial and we decided to make another one so that we can further expand on what we have done and what can be helpful for you to tackle our tasks. So today we will present the DevKit through one of our works which is named CALF, standing for Context-Aware Loss Function. And so it will be a hybrid presentation between codes and scientific presentation, as you will see. So first, an overview of the DevKit. Anthony is going to show you that. So DevKit is definitely all you need if you want to tackle our tasks. We present visualization tools, how to extract features. We present our benchmark codes and maybe a lot of useful functions. So Anthony is going to present briefly an overview of the DevKit.
Yes. So here I'm on the DevKit webpage, which I guess most of you have already seen. And I'm just going to go through some of the useful functions that you can find there that you can use to visualize the data, to extract features on your own game. And then, as Adrien said, we're going to go through one of our work, which is called CALF, and we're going to see a bit the code just to get you inspired if you don't really know how to start. And this might give you some ideas to adapt to your own code. So we can start with the annotation folder right there that has all the annotation and visualization tools that you can use to browse through the annotations. So when you have this new task that you want to handle, it's always great to have a look at what exactly was annotated and what you can expect from the labels that we provide and from the data. And so this visualization tool helps you do that. So what I'm going to do is that I'm going to activate my Conda environment that you can install directly from the folder that I just showed you, but I've already done it just not to waste too much time. And I've also pulled the GitHub repository, and I'm going to go through it in the annotation folder, and I'm going to go to the actions because I want to see the actions first, and in the source where we can find the main code, which is cleverly named main.py. And once you've launched it, the annotator shows up right here. And what I can do is then open a video. So I've just prepared a test match here, which is the remontada, the famous match between PSG and Barcelona. And I can just open the first half of the game, which is 1.mkv, which is the low Q video. And right here on the right, you can all see that I have all my annotations that were done for this game. So I can browse through them very easily. What I can do next is simply play the game. So as you can hear, the sound is also on. This helped the annotator not get bored during the annotation process. And then what you can do to browse through the game is simply to click on one of the actions. So let's say that I want to have the goal that starts at minute 39 and 24 seconds. And right here, as you can see, it directly jumps to this goal. And you can hear the French speakers say that they are mad that PSG got one more goal on their side. So I can browse. This is a goal that was clearly visible. So as you can remind from last week, we have two types of action, the visible ones. And indeed, we can see the goal happening on the screen. And for instance, the kickoff right after the goal was not seen. And it was actually a replay of the goal that was shown during this event. But as we can see, when I will launch the video, the kickoff will have already happened, and so it was annotated during this not shown right there. So the game started again. And if you want to browse through the video, you can also use this slide bar, of course, and you can annotate your own actions if you want to build another dataset or complete this SoccerNet dataset with us, of course. Simply by clicking the enter button, and this will show you all the actions that you can annotate, saying that it's the home or the away team, and if it's visible or not shown. Of course, we recommend you not to do that on our games, except if you find some mistakes, but you can always tell us and we can correct that. But if you want to do it for your own game, you can use this annotation tool very easily. And I have the exact same annotation tool, but now for the replays and the cameras. I'm going to show you that right now. So it's exactly the same annotator, but it's simply in another folder. And I can still find the exact same game. So test match, and I have my first half. And right now on the right, what you have is camera transitions. So here, all the camera transitions were annotated for this game. And you can see the replays are the one with the little left arrows right there. So remember that when a replay is annotated or a camera change, it's always at the end of this. So if I want to get this replay, I just have to go to the previous annotation to get the start. So that was the first replay that we can see. Yeah, otherwise nothing much more to say for this part. It's basically the same as before, so you can also annotate your own camera changes and replay with that annotation tool. So let me get back to the DevKit just a bit, and we're going to go through to another folder before getting back to the presentation, which is called Features, right here. And in there, this is a question that we've had a lot on the first SoccerNet and on SoccerNet-v2 is, can we extract the features, so the ResNet features reduced by PCA, for instance, on our own game? And we very recently provided a new function, which is called Video Feature Extractor right here, so 2 weeks ago, that allows you to actually do that. And I'm going to show you how easy it is. So I will get back to the root of my DevKit right here. And I'm going to activate another environment that is shown here how to create it on the DevKit. And I'm going to launch my function, which is called, so it's in the folder called features, and it's video feature extractor.py. And I'm going to do it for a video that is in some folder that I've already prepared. Then what I'm going to do is that I'm going to add a few parameters. So the path for the features, where to save the features simply. The PCA that I want to use, which is also in the DevKit. This is the PCA that we've used. So if you use this same PCA, you will get exactly our features for the games of SoccerNet-v2 and the PCA scaler, which is the same. And I'm going to overwrite what I've already done because I've already run it a few times today before the presentation. So right there, what it's going to do is going to load, so it's TensorFlow 2 in this case, and it's going to grab all the frames of the video that we want at 2 frames per second. So as you remember, the features are extracted at 2 frames per second from 25 frames per second videos. And once this is done, it's going to simply treat all the videos using ResNet, extract the features, and then reduce them by PCA. And we're going to be able to see I'm just letting this. So in this folder in which I had the video, I'm gonna get, once this is done, so in 24 seconds, I'm gonna get my my NPY file that you can directly load, just as we did. And so this will allow you to, for instance, if you have a train model on SoccerNet and you want to test it on another match, from another league or anything, well, you can directly use that to extract the features. And from what we've seen before, you can also annotate this game if you want to compute some performance on your own data. And so right here I have my test.npy right there. And now I'm just going to show you very quickly a few lines of code just to get you started on how to load these features if you want to if you want to start training networks and stuff like that. So I'm going to get back right here. I'm going to activate another environment, Conda environment, which is the one from Calf that you can also... Oh, we have a bit of a feedback loop. All right. So this is the one from Calf that you can also find on the DevKit. And I'm going to go into a Python environment. So first, what I'm going to do is that I'm going to import NumPy, like always, let's say. And I'm going to load my features using the np.load function. And I'm just fetching one of the .npy file. So it can be the one that you have just created. That would work as well. And I'm just going to show you the shape of this matrix that we just loaded. So this has the shape 5,400 by 512. So the 5,400, the first dimension, is actually the time dimension. So here we have 5,400 frames, which were extracted at 2 FPS from a 45-minute game, so it makes sense because 45 times 60 times 2 makes 5,400. And the 512 features are the features extracted by ResNet that you can find.
After PCA.
After PCA, right here, exactly. And we also provide the non-PCA, and that would be 248 right here. And so that's it for loading the features. And I'm going to show you just a bit how they look like. Basically, it's going to be a set of numbers. So let's say that I will take the 51st features, and I will take feature number 100. Yeah, right there. So it's just a set of numbers that you can directly input into any kind of network, of course. For the labels, now what I'm going to do is that I'm going to import the library called JSON, because I'm going to have to load a JSON file. And this is done very easily with this library, json.load, and we open a file in Python. So very basic. And what is this going to look like? So actually, this is a dictionary that is loaded, which is typical for the JSON format. And this dictionary contains many, many, many annotations, right? And it has this this keyword, which is called annotations. And this is going to be a list of all my events in the game, right there. So I can, for instance, print the first event that happens in the game, which should be the kickoff, of course. And yeah, we have label of this annotation, which is a kickoff right there, which is at 0 millisecond because it starts right at the beginning of the video. It's the home team that shot it, and it was not shown on TV right there. And you also have this game time tag, which gives you, it's similar to the position, which is in millisecond, but here it's more like in a visible format and comprehensive format for us. And it has the half time, so it's in the first half. It's going to be at 0 second and 0 minute and 0 second. If I take the last event that happened in the game now, so it's gonna, of course, happen in the second half at 49:39. It's gonna be a goal, apparently. So the last was a goal, and as you remember, it was the last. It was the last goal at the last minute that saved Barcelona from the 6-1 against PSG, and yeah, it was at this position in millisecond in the video by the home team, Barcelona, and it was visible on camera. So what you can do next is to parse these in some kind of matrix right here, as you can see right there at the bottom of the screen, with zeros and one, with the number of classes as second dimension, and as first dimension, the same kind of time dimension that we have for the features. So what we simply do is create an empty array at first with the different with the size that is the size of the features, and 17 classes, because in SoccerNet-v2 we have 17 classes. And then you can start simply putting one by one all of these events that we annotated inside of this label with simply a 1 at the correct spot. This is something that I will show you very quickly in a following demonstration right after we present the method.
All right, so as advertised, today we are going to present CALF, a context-aware loss function for action spotting in soccer video. So actually, this is a paper that we presented last year at CVPR at the main conference. And so I will present the method here, and then Anthony will present the code that we implemented upon which we built our baseline results for SoccerNet-v2, and that you can also reuse. So it's about the action spotting task of SoccerNet, of course, the original SoccerNet, which means that there are three classes to spot, which are goal, card, and substitution. And so that's the same action spotting task, but with these three classes. So we proposed a module, a network, composed of three parts. The first part is a feature extractor combined with a temporal CNN, then a temporal segmentation module in blue that you can see, and then an action spotting module in green. So the feature extractor is understood as the ResNet extractor that Silvio used for the features with the PCA. And the temporal CNN is one of our small contributions, let's say, because it's just temporal convolutions, so it's not something very difficult. So we will not browse through that, just convolutions in the temporal domain. So we will more elaborate on the temporal segmentation module. So in that module, we take each frame of the video or video chunk that we consider, and we try to classify each frame as belonging to one of the three classes or background. And the action spotting module, which we will explain too, is about really the spotting part, so where the network makes some predictions about where are the actions and which actions are present. So we will insist on these two last modules. So for the segmentation module, temporal context is very useful, and that's what we wanted to do. So as Anthony showed, when you look at the annotations, you have one frame annotated per action, which means that if you represent the actions along the temporal axis, the frames along this axis, you will get a lot of frames with just zero, no annotation, let's say. And when there is an action, you will have a 1, for example, indicating that the frame has been annotated as an action. And that's what we thought as a problem somehow, because you've got all these zeros. So how can you distinguish the 0 just after the 1 from the 0 which is very far after the 1? These are the same value, 0, but they don't carry the same meaning, because a 0 just after the 1, just after the action, represent a frame that still has a lot of cues indicating that the action is happening or has just happened. Whereas a 0 far after the action means that it's just, there is no action anymore, it's not impactful anymore. So we wanted to be able to distinguish between all those zeros. So we decided first to re-encode all the frames, all the annotations, by annotating the time shift from each frame from the action. So for example, if you have the action occurring at this frame, we annotate this frame as 0 because it's the frame of the action, and the frame after will be frame number 1, then number 2, 3, 4, and so on. And the frame just before the action will be frame -1, -2, -3, and so on. So now, when you see a frame with the index 2, for example, you know that it's very close from the action. So there are still cues indicating that the action is occurring. And that's the rationale behind what I'm going to show now. Well, and I will just add, don't worry about the numbers. At some point, they go back to negative numbers, and when there are other actions, everything is smoothly combined. I will show you in a minute. So then we use these time shifts to parameterize the loss function that we want for this temporal segmentation module. So far before an action and far after an action. Well, the action is not impactful on the frames. Far before, you cannot say that the action is going to happen, and far after, it's too late, the action is not impactful anymore. So far before and far after the action, you want a low actionness score. You don't want your network to predict any action. So we will use a loss which looks like this on the left and on the right. So, of course, you want to minimize the loss all the time. So to minimize the loss, you need low actionness score, low predictions. Now, just before an action, you can't predict if the action is going to happen or not. So, for example, think of a penalty which is going to be shot. When you see the player about to shoot the penalty, you don't know if he's going to score or not. So you don't know if there is going to be a goal or not. In some situations, there will be a goal. In some situations, there will not be a goal. So we want to let the network choose whatever he wants as predictions. We don't want to force any prediction just before an action because many similar situations can lead to different outcomes. So just before an action, we say, okay, there is no loss, 0 loss, just like this. But just after an action, when an action has occurred, the frames after the action still carry a lot of information about the action in question. So we still ask the network to predict, not really that there is an action on those frames, but there are some cues. So we want still a high actionness score. So as we want to minimize the loss, we will ask, in this case, to produce high actionness scores, as you can see here for the frames just after the action. And then finally, we have some transition areas in yellow in those places, just to be smooth between far before, far after, just before, just after. So the analytic function that represents the loss is quite complicated. I will not enter the details, but here is the full loss that you can see on the right. So basically, it's usual loss. You see minus logarithm of the prediction or 1 minus the prediction. And for the transition areas, it's a bit smoothed out somehow. You have all the details in the paper, and there are a few extra steps that are performed. It's also in the codes, so don't worry. But it's important to understand this loss. So as I was saying, when you have several events, several actions, because you always have several actions, the time shift encoding makes the loss smooth enough. As you can see on the right, there is no problem between the time shift because the time shift is recomputed as a function of the 2 nearest events, 2 nearest actions, and the index of the time shift is being taken care of. So there is no problem in that sense. So now the spotting module. So remember, the frames are compressed with ResNet and PCA, then fed to the segmentation module, which is temporal segmentation. We combine the features and we feed that to the spotting module, which really performs the task of action spotting. So we feed to the network 2-minute chunks of videos that you can see just at the bottom, 2-minute chunks. And for each chunk, we have several actions, maybe 0 action, maybe 1, 2, 3, 4, up to 5 actions. We conjectured that there is never more than 5 actions in 2-minute chunks. We have to encode the information about the actions that are present within the chunk to be able to compare and to learn the network. So how do we do that? Well, for each action which is present in the 2-minute chunk, we encode an action vector, as you can see here on the right. An action vector here is composed of 5 elements. The first one is a binary indicator, which indicates 1 if there is an action and 0 if there is no action. So for an action vector, of course, you will get 1. Then the second number is a location number, which is between 0 and 1, where 0 indicates the beginning of the chunk and 1 the end of the chunk. So for example, here 0.25 means that there is an action which occurs after 1/4 of the chunk. So after 30 seconds of the chunk. And then, as we have an action which occurs at this location in the chunk, we have a class for this action. So for SoccerNet-v1, there are 3 classes. We have gold, cards, and substitutions. And so, for example, we have a card here. So we encode 1 for the cards and 0 for the goals and substitutions. That's just a one-hot encoding of a class. There is no magic behind that. And so let's say that in this chunk we have 4 actions. So we encode 4 action vectors, and the 5th row remains just zeros. All right? So now our network will output action vectors, which will be compared with the ground truth action vectors. But we will not ask our network to order its predictions. So for example, for 2-minute chunks, we don't want our network to say this is the first, second, third action. That's an unnecessary constraint. The network can predict in the order it wants, and then we have to make the matching. So that's the purpose of this slide. So for example, on the left, we have the network predictions. So we have the confidence score, whether there is an action or not. So you can see that for the first, second, third, and fourth action, well, the network is quite confident, and not so much. The location estimation, and then the class estimation. We will match the predicted vectors with the ground truth action vectors based on the location parameter. Because we want to say, if a prediction is close to a ground truth action vector, then it probably means that they match. The network wanted to say that this ground truth action vector was spotted. So we take the locations that are predicted and the locations which are the ground truth, and we match each action vector to its closest ground truth vector, and then we do the other way around. We match each ground truth vector to its closest, sorry, I forgot to say closest, to its closest predicted vector. So for example, the blue arrows are the matches in the first step, and then the red arrows are the second matches. When we have vectors that match each other, so for example, it's going to get back here. So when we have vectors that match each other, for example, this blue one and this red one, so the first and the second here, we lock them in gray, and then we repeat the process with the remaining vectors. And we can repeat the process several times until all the vectors are matched to each other. So when we have this matching, we can compute the loss. And the loss will be the mean squared error between the vectors that are matched with each other. So it's just element-wise mean squared error. And just note that, for example, for the vector which is matched with the zeros, only the zeros, there is only the confidence score which is evaluated, because it doesn't make any sense to try to evaluate the location, as there is no location. So that's why the blue area here will just encompass this small zero on the bottom left. All right. So that's how it works, basically. And now Anthony will show in the code how it happens.
Yeah, so before going into the demo, I just wanted to give the few differences that we have between SoccerNet-v1 and SoccerNet-v2 here in terms of the network, is that when we went from 3 classes only to 17 classes, we had to increase the number, actually, of predictions that the network can do. So as Adrien said, for the 3 classes, we had only 5 possible predictions, but now for the 17 classes, we have 15 actually. And of course, this metric is going to be wider as well, because instead of having the one-hot encoding on only 3 classes, you have 17. So you actually have a matrix that is 2 plus 17 by 15. So that's just the small difference that we're going to see in there. So I'm going to go to the DevKit now, and I'm going to show you where you can find the different baselines that we provide so that you can get started on your own methods. And I'm going to show you where you can tweak and simply change the layers, change the way the data is loaded inside of these tasks. So all of the codes follow the same structure. So what I'm going to show you for calf also applies for NetVLAD, that is also present for the replay grounding as well. So this is very general. So the baselines are present in one of these three classes, in these three folders. So for action spotting right here, for camera shot segmentation, and for replay grounding. So let's go to action spotting. We have three baselines that we provide so far, but we're going to add some more as they come in, of course. And we have this calf that we're going to check out. So you have everything you need to install the Conda environment that I'm going to use right after, right here, which is very straightforward, like always. And in this source folder, you're going to have a few functions. And we're going to look particularly at three. So the main.py, just to see a bit the arguments that you can directly tweak. Inside of the config folder, I'm going to show you the k values as we had the question, and the dataset and model. So that makes 4 actually. So inside of the config, I'm just going to quickly show you. You have the event dictionary that basically assigns for each class in the label. So for instance, penalty is going to be class number 0. It's just to have an ordering of the class basically. And you're going to have the k values right here. So all the k's for the 17 classes, the k1, then the k2, k3, and k4 right there. So this is just if you want to tweak a bit stuff like right there. So in the main folder, what I'm going to show you is just the parameters that you can directly input, which are right there. I don't know if it's large enough for you to see. Is it large enough, or do I just, maybe I can increase a little bit?
That is even better.
That is better? Right, perfect. So this first argument, you always have to put it. Of course, it's the path to the SoccerNet-v2 dataset. So this is the path from which you downloaded, in which you downloaded the dataset using the pip package that we showed in the first tutorial. So make sure to check out the first tutorial if you've missed it. You have the features right here that you want to use. So for instance, the ResNet PCF 500.12. What we use is ResNet TF2 PCF 512, basically. The maximum number of epochs, that's very basic. If you want to start with a pre-trained network instead of training from scratch, you can directly put the weight path in there. The model name, which is going to create a folder in which it's going to save the results. And this model name will be the name of the folder. So if you have to make several experiments in parallel, simply change between them the name, and it won't overwrite the previous result, of course. This test only we will see a bit later, and this challenge is for producing the prediction files on the challenge set that you can then upload on Eval AI. Yeah, so basically afterwards, all you have are parameters that are related to the training and to the network itself. I'm going to just go to this receptive field parameter because we're going to have to use it, unfortunately, for the explanation later. So I'm just going to go a bit into the detail here. But this receptive field is the temporal receptive field of our 3D CNN, which convolves temporally the features. Because at the limit of the chunk, it's going to have to use padded values, of course. And so this receptive field tells us how much of the features of the predictions at the end used padded values at the border. So that's just a little detail that will be important later on. So what's important for you is how we load the data. And if you want to use our data loader, that's totally fine. So for instance, here we have created a SoccerNet clips class, which is actually our data loader for training and the validation loss. So for training the network and experimenting on the validation loss. So right here, what it's gonna do, this data loader, basically, it's gonna create the clips, so the 2-minute chunks, and you can simply change the size of the chunks right here by changing this parameter. And it's gonna do that with the receptive field that I talked about, because outside, it has to know that at the borders of the chunk, it should not apply the same kind of loss than in the middle of the chunk where we have all the information. So right here, we are loading the features as we've done before. We are loading the labels, and this is the parsing of the labels that I was talking about, that I was going to show you later. So this, we iterate through each annotation inside of our folder, inside of our game, and we're going to retrieve the time, which event was done, which half time does it correspond to, the minute and seconds, and then we transform that into frame index, of course, because we have to go through from an annotation that is either in millisecond or in minute and seconds to a frame index, and that's how we do it. And we use the dictionary that I showed you before to state on which line of the label it should go. So between 0 and 16 for the 17 classes, basically. And right after, we compute the one-hot encoding to the shift function that transforms these zeros and 1 into the shift between the action that Adrien showed you. So you can reuse this function if you need it, and this entire class as well. And then basically what it's going to do is each time we want to fetch a batch, it's going to select several chunks and put them into a batch. And just this is something that is a bit was a bit left out of the paper. So, but I think it's interesting to state it here, is that the selection process of these chunks are important, because if you select randomly the chunks, you're going to, for the 3 classes, for instance, you're going to get mostly background inside of your chunks, because goals, cards, and substitution do not happen that often. And even for the 17 classes, there are going to be some actions that actually won't be very much shown inside of your chunks. So balancing your chunks is important in terms of classes as well. And this is what it's basically doing. It's going to go around each type of action at the same proportion. So for instance, it's going to at least retrieve one goal once every 17 chunks, let's say. And so you can also reuse, of course, all of this code. And finally, if you are simply interested in changing our model because you think you have a better idea, you can directly go into this models.py file, in which we have our model, which is basic PyTorch model, very basic PyTorch code right there. So defining all the layers here in the segmentation module, in the detection module, the outputs, of course, and then doing the forward parse, in which we do these computations. So don't hesitate to take a look at what we have right here and to simply change it if you just want to get started and see if you can have a better idea. All the code should work the same if you only change this model and you respect, of course, the input and outputs that we provide. So yeah, now we will just see very quickly how to do the inference on the test set. So we have our entire video right now, and we want to predict everything. So we have the segmentation and our detection outputs. So how do we do that? As I said, we don't want to take all of the information that is inside the chunk, because at the border, it's going to use padded values, which are 0 padded. And so it's not going to have the same information as the middle of the chunk. And so what we are actually doing is some kind of repetitions in the chunks. So you can see that our first chunk right here is only using the first part of the chunk, because of course, before the video, we cannot create information, so we have to use what we have. But for the second chunk, we're going to use not the chunk that comes right after, but a chunk that is a bit overlaid on the previous chunk, so that the useful information actually follow one another, which is a shift of the receptive field in total. So because we have the receptive field before and have the receptive field after. And then what we can do is simply reorder them, these useful information, use them to have our app output right there. But in terms of network, what we're going to do is that we are first going to stack all these useful information, 1, 2, 3, 4, 5 chunks, as a batch. So which is going to be a batch of around 33 to 36, 37 chunks, depending on the length of the game. And we're going to get it through a network to get our segmentations first inside of the useful parts that we can then simply concatenate to get our entire segmentation. But of course, the task is detection right now for SoccerNet-v2. Segmentation is just there to help the detection actually. And so for each chunk, we're going to get a detection, which is going to be the famous matrix that we presented right after of 2 plus 17. So confidence score, location within the chunk, and the one-hot encoded 17 classes. And it's going to be, in the other dimension, the number of prediction, which is 15 in our case, but which could be anything else, of course. And so this is if we want to infer on the test set. So once you have the entire video and you just want to get your detections on this video, which is the case that is interesting to us. But let's say that, I don't know, maybe some of you are working in the industry and want to do this for a live game, all right? So you cannot wait for the entire game to end if you want to get during the game the information, of course. And so we propose a way just to do the inference on a live game, which is exactly the same as the test set. But right now, what we're going to do is that we're going to take it chunk by chunk, of course. So for the first chunk, we will have to wait 2 minutes to do our predictions. And right after, we will have to wait for the 2 minutes minus the receptive field to get the next predictions that are right there. And this actually introduces only a delay, which we can directly control by the chunk size and the receptive field. So right here, for instance, in our case, we have a 100 seconds delay, which is a bit less than 2 minutes. So if this is great for your application, then you can apply it directly right there. But this is more for commercial use, and it's not really related to the challenge, let's say. So I've got right there a command, which is main.py, as we've seen, that will train the network. And I just have to add a few arguments to make it work. So of course, the SoccerNet path right here, which is my local SoccerNet path, and the features that I want to use, so the ResNet TF2 PCF 512 features. So once I hit enter, so this is all running on my laptop, so it should be running on any device, let's say. It's going to take just a bit of time to load the data. So as you can see, like 4 minutes to load the 300 game of the train set, that it's going to load the validation set, and so on. And what it's going to do is that it's going to, right there, I'm going to go here in the models. So it's going to create this calf because it's the name by default. And inside of there, it's going to create a log file with everything that is happening. And we are going to get the weights of our network in this folder once this is done. So of course, I'm not going to go through the entire training process, which takes about 2 to 3 hours in total on my laptop. But I'm going to show you with some pre-trained weights that we have and that we provide to you that are in calf benchmark right here, the model weights. So what you can do is use the same Python file to test the network. So what it's going to do is that it's going to also load this our dataset with our ResNet features, and it's going to fetch the calf benchmark folder, and we're going to say we want only to test, not train. And so what this is going to do, it's going to load all 100 games of the test set, which is a bit faster here. And then it's going to compute the average MAP. So in a few seconds. And in the meantime, I will show you, in the outputs folder, what's going to happen is that it's going to write the predictions in there. All right. It's going to write all our predictions inside of this folder in the same folder architecture as the dataset. So if I go here, I can find my game Barcelona PSG with my predictions right there. So these are all the predictions that he's done. So for instance, in the first half, at the second 24, he thinks that there is an indirect free kick with a confidence very low. So actually, this is not a prediction, of course. But right here, 50% confidence that at 1 minute and 5 seconds, there is a clearance. And so if you want to then submit these files to the server, all you have to do is right-click, compress, and then send in the zip folder. And so as you can see, it has computed the performance, which is around 41.6% in our case. And to finish, I would say that you can use the function that we showed in the first tutorial right here, where your prediction path is this folder, of course, and this it won't have to reload the network and everything to compute the metric, but it will compute the metric directly based on the predictions that were saved that we've just seen, and it's going to show us the exact same results, of course.
All right, so to finish with the results of the paper, which is from last year, we reached 62.5% on the SoccerNet, original SoccerNet, and we also tested on ActivityNet on top of BMN code, which was state-of-the-art at the time. And so we developed a new state-of-the-art, as you can see. But now we have been completely crushed by Mahazni et al. And Tomei et al. So Matteo, I think he is on the Discord channel, which is great. Exciting results that are coming on SoccerNet-v1. You can see on the right some example of visualization of the results. So the green stars are the spots that we predicted, the blue bars are the ground truths, and the orange curve is the segmentation curve of the network. So as you can see, for the goals in this case, we spot correctly all the goals. For the cards, there are 2 missing cards, and for the substitutions, there are 2 false positives. And one thing that we noticed, which was quite interesting here, was that we could also notice some goal opportunities and unsanctioned fouls. So actions that are not annotated that we could recover in our results without them being spotted, which was quite interesting. It's interesting because from that, we could derive a very simple highlights generator by just selecting on the temporal segmentation curves the interesting actions, so those with a high segmentation peak, even if they were not detections, spottings that the network wanted to detect. So in this case, we have cards due to foul, cards due to simulation, we have goal opportunities, free kicks, and so on. Goal on free kick, goal on penalty, and regular goal. So, of course, we are interested now in SoccerNet-v2. So what about the results? So Anthony just showed 42.6, I think.
41.6.
41.6. So our result with that network calf on the challenge set is 42.22. And when we developed the baseline, we thought, okay, that's kind of good. Let's see what happens. Maybe people will have hard time beating that, which turned out to be completely false because, as you can see, we've been crushed completely again by already 3 teams. So Ivory Coast, I have a black screen. Okay, Ivory Coast, Visual Analysis of Humans, and AI Image Lab RMS. So congratulations at the moment for these teams. We will not try to develop a new baseline to beat that, of course. We let you make your own competition between you. And it's very important also to note that the best result that you can see on Eval AI is not the actual best result that is submitted. So when you submit a result, you may want to get it private. And we will respect the privacy of these submissions, but we will notify you on Discord, that's exclusive content for you on Discord and on these videos, the true leaders, the actual metric of the true leader. And so we don't say who, but the 60% mark has been reached for the average MAP. So currently the best average MAP on the challenge set for action spotting is 60.32. So don't think that if you have in your computer something that produces maybe 58, 59, you will be the first, because there is a high mark to beat here. So that's very important. And so the challenge is getting very exciting also. So to conclude, maybe just recap, we have a great challenge, which is still 1 month to go. So it ends at the end of May, so 1 month. We have prizes of $500 for the 2 tasks sponsored by Second Spectrum. And as you know, we ask that you provide a report of maximum 2 pages at the end. We didn't specify that, but for the report, you have 1 more week, of course, because if you are still fine-tuning the network and so on until the very last day of the deadline, we don't ask you to send us the reports on the same day. You can take a few days rest and then write the report. So you have 1 more week. There is no problem. That's good. We're good to go. So see you next week. It will be on Thursday. We will write that in Discord, no problem. We will send a new link, as always. And then, see you on Thursday then. And hopefully we will see a lot of you and a lot of submissions. And good luck with the competition.
Bye.
Thank you. Bye.
Thanks. Bye.
Bye, everyone. Thanks, guys.